Hello everyone, welcome to my presentation. My topic is monitoring gate events by image processing. I'm Jeffrey Young, and my supervisor is Dr. Milena Simic and Dr. Milan Simic. This application could be used as a daily gate self-monitor app on mobile phone without any wearable sensors or any other medical devices necessary. This application includes a novel foot progression angle, we call it FPA detection algorithm, and a novel foot flat face detection algorithm. It possibly can be developed with feedback system to I would like to take this opportunity to thank my supervisors for their patient guidance, encouragement, and advice they have provided.
Let's begin with a movie star. Charlie Chaplin was a famous movie star for his funny walking manner and overstated toe-out angle. One medical research, gait modification, named a walking manner after his name, called Charlie Chaplin gait.
Gait modification. The gait modification plays an important role in orthotics, prosthetics product, biped robot, and exoskeleton application. The most important parameters of gait are foot progression angle, foot flat face, step width, step length. The foot progression angle is defined as the degree of external rotation of the foot with respect to the direction of progression. The foot progression angle is measured at foot flat face stance only. The accuracy of foot flat face detection is critical for foot progression angle measurement. The foot flat face has an important function since body weight is transferred to the lead leg at this point and must absorb this weight while maintaining forward momentum. The step width, step length, and step speed. All these parameters calculation is based on this foot flat face stage. The traditional gait laboratory is a gold stone in monitoring gait parameters, but it's occupied exclusively for one participant at a time, and the cost is very high. The downward-facing camera is mounted on the participant's upper body or torso via a harness shown in the picture. The camera does not have to be perpendicular to the walking plan or any reference. Any people can wear it on without calibration or technician support. After wearing the harness, a 10 picture was taken from different angles on top of the calibration checkerboard to calibrate the camera lens and remove the lens distortion. The rectified image allows metric properties such as planar angles to be measured from those perspective images. In the validation test, the angle between the two strips was detected accurately with average error minus and plus 0.05 degrees through the chest and mount the camera simultaneously. In the nature walking speed, there are 3 stages within each footflight phase. The third stage has less impact from the ground, a lowest speed, better view catchment, and better image quality. Therefore, we measure all the gate parameters mostly in this stage. In the video stream, the photos were filmed in 30 Hz frequency. In the 2 successive images, the image features were matched and compared. Therefore, we can calculate the displacement of the features in 2 successive images. Based on that, we can calculate the speed of the moving object in the video. Now, we can summarize the full professional angle algorithm as shown in the flowchart. In this page, there were 4 groups of data and the image was shown in the sequence of the frame index in the video. From the left top corner, we can see the frame index is 944. This image was shot at the early stage of the foot flight phase. At this stage, we can see the body trunk 3 angle is 12.67 and the foot speed is 35 centimeters per second. This means the foot is still moving, so we don't accept the data on this stage. On the left bottom corner, we can see the foot speed is dropping by 5 centimeters per second. Actually, at this stage, the foot is almost flatly on the stage because the ground force impact to the body and the calculating errors, they told us the foot speed is still moving. So as soon as we set up the straight hold to eliminate the calculating error or the camera impact parameters, we accept this one as foot flat phase beginning. At the right top corner, we can see the foot speed almost dropped to 0. At this stage, the foot variation angle is 19.4. At the right bottom corner, we can see the foot speed is absolutely 0. This means at this stage, calculation is very stable because no ground response force apply on the body, and this time the body's speed is low. You can see the camera position right on the top of the supporting foot. This is the best stage to take the picture and take the calculation of all the gate parameters. So in each stage, we detect the foot flight stage from the frame 944 to the frame 1000, and we collect all of the image and the data. And after analysis this data, we take the best result at the foot speed equal to 0. Normally, at each step, we can get more than 10 pair of images with the foot speed calculate equal to 0 or minus plus 5. So we get the average of the foot speed and the other parameter matters in the average value to accurate the result. In the body-worn camera system, ground and foot moves respect to the camera with different speed. When both foot speed and ground speed are same, this means foot are flatly on the ground. This means its foot at this stage. So in this picture, we can see when the supporting foot is foot speed and ground speed are detected and calculated. The difference or the offset of two speed is shown in the purple color. When the purple line is getting to 0, as shown in the stage 4 and the point D, we can find the speed of foot and the ground are same. Also, at this stage, their speed is lowest. So, we pick up the gate parameters from this point. This is the algorithm we detect the foot flat face and measure the foot projection angle. During the normal walking speed at point D, there are 4 or 5 pairs foot projection angle were measured. Their average value will be taken as the foot projection angle of this step.